Hi guys, welcome back to Unit 12 of Kinetics. So let's go ahead and make sure that your name is on your packet and your class period, whether it's first, second, or fourth, or maybe you're in another chemistry teacher's class, in which case you don't have to do that. But if you also go to Meadow Creek, you can always stop by my room and I can give you a copy of this packet if you don't have one. So one thing that we want to talk about is when we're talking about kinetics, the reason why it's called kinetics is because we're talking about movement and things of that nature. And specifically in chemistry, we see energy represented in two different ways. So kinetic energy, again, connected to the word kinetics, which is the overall topic of this unit. Kinetic energy is the energy of movement. And so when we think about it, all atoms are moving. Okay, and so they all move, they're always vibrating. There's never a point where they stop moving completely. Even solid atoms, think about it. Feel the table that's next to you, or the chair, or the bed that's underneath you, wherever you're watching this. And the atoms in there, even if it feels completely still, are actually moving. Okay, and so potential energy is, a lot of times we learn about it in middle school physical science as being stored energy, and it's energy in chemistry in the bonds of atoms in molecules, right? So if I have carbon dioxide, or let's just draw, yeah, we'll draw carbon dioxide, two oxygens. Okay, so in this double bond here, there's energy. And so what this means is that to break bonds or to form bonds, energy is going to be required. And so breaking and forming the bonds between atoms and then between protons and neutrons in a nucleus, that's how a lot of things work, and that's also how nuclear energy, they're trying to make that a more usable energy source. And so when we're talking about movement, we're talking about how atoms move, and in that movement, how do they react? And so we have this really important theory that we need to go over. It's called the collision theory. And so what the collision theory says is that reactants must collide, okay, which makes sense based on the name of this theory, with enough energy to form the products. And what it should say is with enough energy and correct orientation. And I'll explain what I mean by that. We're going to break it down. So when we talk about orientation, okay, we mean that the atoms must align properly. If they don't, then they will bounce apart. So they will bounce, which that bounce apart is called an ineffective collision, okay, because they collide, but there is no reaction happen, so it's ineffective. It's a waste of time. So let's look at what this might mean. So if I have, let's say, two atoms, and one is A and the other is B. That's what I want to make, right? Well, let's say I have atom A, okay, and I have another molecule, but it's BC. Well, if atom A were to collide with atom B right here, okay, they could, in theory, form this compound, right? But if we have the same atom, atom A, but we switched C and B, they were oriented differently. Maybe someone turned them around in space, right? If A were to hit here, well, then they couldn't form AB So they would just bounce apart. That would be an ineffective collision. Okay. Another thing that the collision theory says, it has to have enough energy. This is called our activation energy, which is abbreviated as a capital E for energy and a subscript A for activation. And it's the minimum amount, so minimum amount of energy required to start a reaction. Okay, so minimum amount of energy required to start a reaction, and what happens is when that activation energy is reached, a transition state will occur. And this is the compound that is created in between the reactants and products. Okay, so let's look at what that looks like for endo and exothermic reactions specifically. In our last unit, we talked about energy diagrams that had potential energy on the y-axis and the progress or time of the reaction on the x-axis. And so the first one we're going to look at is an we don't need two E's, is an endothermic reaction. Now remember that an endothermic is something that absorbs energy, right? So the system absorbs it or it goes into it. And so this means that if you were to write a reaction, let's say A plus B produces C, okay? That means energy is written as a reactant, okay? Because energy is going into this reaction. Now, if we look at something, at an energy diagram, okay, your reactants at the beginning, A plus B, okay, they have a certain amount of potential energy, okay? So this would be called our delta H of our reactants, okay? That's because there is a certain amount of potential energy stored in the bonds of molecule A and B, or atom A and B, okay? Now, what happens is that energy that was a reactant gets absorbed, and so the potential energy starts to increase, okay? And what happens is when they get to the top of this hill, it starts to crest over, and they start to release energy a little bit. That amount of energy from the top of this hill all the way to the reactants, that's our activation energy, or E sub A. And so this activation energy is the energy required to start the reaction. So if I do not get all the way to the top of the hill, the reaction will not occur. Okay, and so that's really important to understand. And so then the reaction will start to release a little bit, and then our products will form. And in this case, it was a synthesis reaction, so we just have product C. And so this, from the top line where the product is down to 0, that is my potential energy, or delta H, of my products. And so last semester, so these kind of blue labels are things that are a little bit new, but last unit in thermo, we talked about how if you drew an arrow from our reactants to our products, we see that it goes up, or it's positive. And this was talking about our delta H of the reaction, and the word reaction is abbreviated RXN. And so what this means is, in order to get that answer, we can say that delta H of our reaction is equal to delta H of our products minus delta H of our reactants. We take those two things and subtract them. Remember that this triangle is the Greek letter delta, which means change in. And we saw that in our last unit with Q equals mc delta T, or the change in temperature, which was final minus initial. Well, our products are what we end up, they're our final, and our reactants are our initial, what we start with. And so that's what we see there. And so all of this shows, now at the top here of our hill is where we're going to see our transition state. So kind of right about here in this time frame, in between where we no longer have AB because we've started to react, but we don't have everything as C yet. What you'll kind of begin to see is A and B are separated, so you'll just kind of have this A-B kind of complex before it turns into C. Now, another way of showing that reaction is if we look down at our exothermic energy diagram, okay? So if we were to make a diagram that was exothermic like this, and let's go ahead and label. Remember, exothermic is the opposite of endothermic. Instead of absorbing energy, it releases energy. And so let's say we have the reaction A plus BC produces AB plus C. Okay, so we have a single replacement reaction, or as I affectionately call them, a home wrecker. And so we see that at the beginning, we have A plus BC here, okay, and there's a bond. This is a bond between those two, okay, not a subtraction sign. So actually it would be more accurate to just write BC like that, and then AB. Okay, so we have BC, and then we have AB plus C down here. Well, in your transition state, okay, up here, you're going to find that A is going to start to form a bond with B, and its bond with C is going to start to break. And so you're going to have this like combination between everything where it's like halfway, excuse me, where it's halfway there, it's not quite. This compound isn't seen at the beginning or at the end. It does like completely transform, and that's why it's called the transition. It's only there as things are moving and changing. And so here we can see that our delta H of our reactants is much higher than it was for an endothermic reaction, whereas our delta H of our products is much smaller. And so what that shows us is that if we were to look at our delta H of our reaction, we see that this is negative, right? And that's delta H of our reaction. So our delta H of reaction is going to be our delta H of our products minus the delta H of our reactants. And because our product value is going to be so much smaller than our reactant value, that's how we get this negative number here. And if we were to look at the activation energy, we can see top of the hill down to the reactants, our activation energy in an exothermic reaction is much smaller than an endothermic reaction. And so this is kind of what you want to be aware of with the collision theory and how atoms have to have the activation energy to get over this barrier. Think about it as a hill. If you're running a race, if you have not put the right amount of protein and carbohydrates and hydration into your body, then you are not going to have the energy to run up this hill, right? So the bigger the hill, the more energy is required for you to actually make it to the end. And so the orientation and the energy is what you're going to need there. And you can see that with the matches demo that we did in class. So the main thing that we did was we took, and I'll do my best to explain it through this video, is we had a matchbook. This is my drawing here. It's not perfect. So this is matches, and everyone knows that in a matchbook there's like a rough side of the box, and that's what you strike your match next to. And your match is kind of like a wooden stick, and our matches for some reason had a green tip, instead of a red tip. That was interesting. And so what I did was I took the matchbox and the match and I oriented them in different ways. And I said, okay, what happens if I take this end and I hit it against this part of the matchbook? And I would hit it really, really hard and it would not light. And then I would say, okay, well, um, what if I take this end, the green or red tipped end, and I still hit it against this part? Well, now my match is aligned correctly with where I want, but my matchbook isn't. And then, so we could see that our orientation really mattered and how the correct orientation would be to have this green tip against the rough part. And now if I lightly took the match and I barely touched it, it was aligned correctly, but I barely scratched it, then it would still not light. And that's because it didn't have the activation energy needed. And so when the demo says to explain in complete sentences using the terms orientation and activation energy to explain how to light a match, we know that a match has to have the correct orientation and must be struck with enough force to have enough energy to overcome the activation barrier in order to light. And if the orientation or if the energy are not met, those are the conditions we were talking about, then the match will not light. And so that's important to understand. And so in our next video, we'll come down here and we will talk about reaction rate and what that looks like.